All right, Class 6, Chapters 10 and 11, Worksheet, YouTube video. Chapter 10 is Independent Measures T-Test. Two rival college fraternities brand themselves on riding off-road vehicles. Fraternity A's vehicle of choice is the ATV, the all-terrain vehicle. Fraternity B's vehicle of choice is the dirt bike. Each fraternity claims that their off-road vehicle of choice is faster in a mountainous terrain setting. They took their 15 best riders each and faced off. The goal was to have the fastest average top speed on a mountain trail. All 15 riders from each group's top speed were measured. Fraternity A's 15 riders finished with a higher average top speed. Is the ATV significantly faster in the mountains than the dirt bike? Use an alpha level of 0.01 to answer. So we're given some data here. We're given fraternity A's N, which is 15, mean, which is 40.8, and sum of squares, which is 510. We're given fraternity B's N, which is 15, M, which is 34.0, same as 34, and SS, which is 414. So in this case, the null hypothesis would be ATVs are significantly slower in the mountains or the same as dirt bikes. Again, the opposite of what the research will be, which is ATVs are significantly faster in the mountains than dirt bikes. So in the null here, we put slower or the same, right? Because you've got to think about the middle of the distribution and the opposite side of the distribution. And the research is looking for the right side of the distribution to be significant. One-tail or two-tail test. One-tailed and faster gives that away because it's giving a direction. Independent variable is off-road vehicles, and the two levels of that is level 1 ATVs and level 2 dirt bikes. And the dependent variable is speed. So DF1, so DF of group 1 had 15, so 15 minus 1 is 14. DF2, fraternity B, they had 15 as well, minus 1 equals 14. DF total, you just add the two up. 14 plus 14 equals 28. And then the critical T value, you use the DF total, which is 28, the alpha level of 0.01, and how many tails, which is one tail. And when you go to the chart, you'll see that that is 2.467, and you just have to pick if that is a positive or negative. So I give you two formulas for DF total, which can either be N1 plus N2 minus 2, or DF1 plus DF2. The population mean difference is always 0, okay? That comes from a null hypothesis saying that there would be no difference between these two populations, the populations of ATV riders and dirt bike riders. A sample mean is given of 40.8, the sample mean 1. Sample mean 2 is given for group 2 of 34. The sum of squares for group 1 is given 510, and the sum of squares for group 2 is given 414. Sample variance of group 1. Take the sum of squares of group 1 divided by the degrees of freedom of group 1. 510 divided by 14 equals 36.43. Sample variance of group 2, the dirt bike group. You take the sum of squares, which is given 414 divided by their degrees of freedom, which is 14. So 414 divided by 14 equals 29.57. Now we have to pool the sample variances. So you do that using this formula right here. Now, and you see in the work, I like to do everything step by step so you don't make a calculation mistake. So what as I do is I take the DF of 14, which is DF1, times 36.43, which is the variance of group 1, plus DF2, which is also 14, plus the variance of group 2, which is 29.57. Divided by df1 plus df2 equals. So this first part in the parentheses equals 510.02 plus 413.98, which equals 924. So 924 divided by 28 equals 33. The pooled variance is 33. Now we have to get the standard error of the mean difference. So the first thing you want to do is do everything that's inside of the square root sign. So I first do 36.43, which is the variance of group 1, divided by n1, which is the n of group 1, which is 15, plus 29.57 divided by 15. And that equals 2.43 plus 197, which equals 4.4. So do that first, and then the square root of 4.4 is 2.10. T obtained. Mean 1 minus mean 2 minus mu 1 minus mu 2. Well, the population mean difference is always 0, okay? So right here. So the population mean difference is always 0. So this part of the equation, you basically don't even need to look at, okay? All you need to do is do mean 1 minus mean 2 over S of M1 minus M2, which is 40.8 minus 34.0 divided by 2.10, which is this value right here for S of the mean difference. And when you do those calculations, you will get 3.238. So now the decision on null hypothesis, we have to compare that 3.238 to the critical value, which is positive 2.467. So do we beat it? Yeah, we do. 3.238 is bigger than that value, so we reject the null. Now we want to see the Cohen's d effect size. All right, Cohen's d effect size is always reported in APA when doing an independent means t-test. So that is the one that I'll have you compute while computing t-test for independent means. And that is simply M1 minus M2 over the square root of the pooled variance, also known as S squared P. So you just do the deviations from the mean, 40.8 minus 34.0 divided by 5.74 equals 1.18. Well, if a large effect is 0.8, a 1.18 would be a very large effect. Moving on. 20 students randomly assigned to an experimental group receive an instructional program. 30 in a control group do not. After 6 months, both groups are tested on their knowledge with a knowledge test. The experimental group has a mean of 38 on the test with an estimated population standard deviation of 3. What does that equal to? That equals to S. The control group has a mean of 35 with an estimated population standard deviation of 5, again, equal to S. Is there a difference between the two groups' knowledge? Using the 0.05 level, what should the experimenter conclude? So is there a difference gives away that it's a two-tailed test. So the no would be there is no difference between the knowledge of the control group and experimental group. And the research hypothesis would be there is a difference between the knowledge of the control group and the experimental group. One or two-tailed test. Two-tailed, again, the key word is difference. The independent variable here, what is being manipulated? The instructional program. And the two different levels are the group that was given the instructional program and the group that was given no instructional program. And the dependent variable, knowledge was tested. So that is a dependent variable because knowledge was measured. All right, DF1, well, there was 20 in group 1, so 20 minus 1 is 19. There's 30 in group 2, 30 minus 1 is 29. Add those up, 29 plus 19 equals 48. So we use degrees of freedom total, and we know that it's a two-tailed test at 0.05. So what you do here is you go down, and you will see that there is no 48 on the table. So you have to use the number that is above what's in between. So you'll see there's a 40 and a 60. So you must always use the number 40. This won't be on the test, but just so you know, because you want to underestimate, right? You want to basically give a bigger critical t-value, because as degrees of freedom goes up, the critical t-values goes down, okay? So in that case, you are going to use the degrees of freedom that corresponds to a DF of 40. And that would be plus minus 2.021. And again, use the lower number, right? So if this falls between 40 and 60, use the lower number. Even if the number was 59, if it's not quite 60, you would use the one above it, which is 40. Population mean difference, again, always 0. Sample mean, given, 38. Sample mean 1. Sample mean 2, given, 35. Sum of squares, 1, not needed. Sum of squares, 2, not needed. Why? Well, we're given the estimated population standard deviation, right? That's 3. It was given to us in the text. So to get the variance of group 1, the sample variance of group 1, all we need to do is the variance is the standard deviation squared. So 3 squared equals 9, and the same applies for the sample variance of 2. 5 squared equals 25. The pooled sample variance. All right, so now you have to do the pooled for this one. So again, do it step by step. Take the DF of group 1, which is 19, times the S of group 1, which is 9, plus DF of group 2, which is 29, times the S of group 2, which is 25. And that equals 171 plus 725, which equals 896. So 896 divided by 48. 48 is DF1 plus DF2, or DF total, same thing. So the pooled variance is 18.67. Now, to get the standard error of the mean difference, you simply take the variances. So the first step is do everything that's inside of this square root sign. So we want to do 9 divided by 20, because 9 is the variance for group 1, and 20 is the n for group 1, plus 25, because that's the variance of group 2, divided by 30, because that's the n of group 2. And you'll get 0.45 and 0.83. Add them up, you get 128. So now, square root 1.28, and you will get 1.13. T obtained, again, you don't have to look at mu1 minus mu2, because we know that always equals 0. So all you need to do is mean 1 minus mean 2, 38 minus 35, divided by 1.13, equals 2.655, and 2.655 compared to 2.021, are we failing to reject? No, we are going to reject. I will fix that on the answer key, but this is wrong. We reject the null hypothesis, because if the t obtained of 2.655 is bigger than a plus minus 2.021, then we know that we must reject the null hypothesis. Okay. Now to get the estimated D, you simply take mean 1 minus mean 2 over the square root of the pooled variances, which is 38 minus 35 divided by 4.42. All right, after you square S2P, you will get 4.32, and 3 divided by 4.32 is 0.69. All right. So a top to bottom, chapter 11, repeated measures t-test. 5 people who were convicted of speeding were ordered by the court to attend a workshop. A special device put into their cars kept records of their speeds for 2 weeks before and after the workshop. The maximum speeds for each person during the 2 weeks before and the 2 weeks after the workshop are as follows. Using the 0.05 significance level, should we conclude that people are likely to drive more slowly after such a workshop? So what's the independent variable? Workshop, right? The 2 levels, attended the workshop and did not attend the workshop. The dependent variable here is speed. You could put miles per hour, that's fine. So the research hypothesis, those who attended the workshop drove slower after the workshop than before, right? That would mean that it worked. And the opposite of that is those who attended the workshop drove faster or the same than before the workshop. Again, a directional hypothesis, so you must state the opposite and the same in the null. So now we need to get the mean difference and the sum of squares. So the way you do that is you take this chart and you plot all the numbers. So you plot the before scores and the after scores. And that comes directly from here. I just copied them in. And now you do after minus before. 58 minus 65 is -7. 65 minus 2 is 3. 56 minus 60 is -4. 66 minus 70 is -4. 60 minus 8 is -8. If you add those up, you will get -20. -20 divided by 5 is -4. So now what you do is you take what you can think of x, but x is going to be what is right here, right? So that can also be labeled as d, okay? So you take d minus md, or the after minus before scores, just keeping it as x because we are very familiar with x, and you do -7 minus 4. So when you do a negative minus a negative, the 2 negative signs next to each other equal positive. So it's like saying -7 plus 4 equals -3. 3 minus 4 is -1. -4 minus 4 is just like saying -4 plus 4, which is 0. Same goes for the next one. And -8 minus a -4, those minus signs combine and turn to a plus, which equal a -4. Now you square them all. 3 squared is 9, 1 squared is 1, 0 squared is 0, 0 squared is 0. -4 squared is 16. You add those up. Now you have the sum of squares of the mean difference. Okay? So right here, the mean difference is -4. Okay? And the sum of squares is 26. We got that from the table. All right, the estimated variance is the sum of squares divided by n minus 1. So 26 divided by 4 equals 6.5. And then to get the standard error of the mean difference, you take the square root of the variance divided by n. So first, 6.5 divided by 5 is 1.3. So the square root of 1.3 is 1.14. The t critical, well, df, we know it's 1 tail. df is 4, 1 tail alpha of 0.05. So if you go to 0.05, 1 tail, df of 4, you'll get a 2.132, right? But we're looking to see if the drivers drive slower, so we are going to use the negative of that number, and your t critical will be negative 2.132. T obtained, similar to the independent test, the mean difference, which is the mu difference, the population mean difference, is under the null going to equal 0. So this means nothing as far as solving goes. Maybe it'll be a multiple choice question. And it will be -4 divided by 1.14, which equals negative. I wrote negative because on the computer you can't really see the negative sign. So it's negative 3.509. All right, r squared, you simply take the obtained t value, square it over the obtained t value squared plus the degrees of freedom. You should get 12.313 divided by 16.313, which will come out to 0.75. And a decision on the null here will be reject the null. Let's check. Our obtained is negative 3.509, and our critical value is negative 2.132. Negative 3.509 is more extreme of a score than negative 2.132. So we reject the null hypothesis, and we can also say r squared, we could say 75% of the variance can be explained by the manipulation of the independent variable, which was that course that helped drivers drive slower, which they put the speed detector in their car to check their speeds. Chapter 11, more of how it will look on your test. That's really to let you know what goes on behind the scenes. Now, let's do this one. So 5 sophomores were given an English achievement test before and after receiving instructions in basic grammar. The mean difference score is negative 40, or negative 0.40, and the estimated variance for the difference score is 8.3. Using the 0.05 significance level, is it reasonable to conclude that future students would show higher scores after instructions? Higher, one tail. Independent variable is the instructions in basic grammar. Level 1, given test before instructions in basic grammar, and level 2, given test after instructions in basic grammar. Dependent variable would be scores on the English achievement test. So the research hypothesis. Those given special instructions after the English achievement test will score higher than they did before given special instructions. Null hypothesis, opposite that. Those given special instructions after the English achievement test will score lower or the same than they did before given special instructions. Mean of the difference, negative 0.40, given, no need to solve. Estimated variance, given, 8.3. Estimated standard deviation of the mean difference. So all you do is you take s squared divided by n first, which is 8.3 divided by 5, which equals 1.66. So the square root of 1.66 is 1.29. T critical is, we use a degrees of freedom of 4. Okay, there were only 4 participants. All right, didn't mention this in the last question. Even though they're tested twice, you don't count them as 2 individuals. If one individual tested twice, the degrees of freedom stays as if it was one individual. So the n equaled 5, so df equals 4. It's one-tailed positive, right? Because we want to see if they did better on the test, the alpha of 0.05. And if you do what we know what to do on the t chart, you'll get a t critical of 2.132 and have to choose a positive or negative. We choose a positive. Therefore, the t obtained is the mean difference, which is negative 0.4, divided by 1.29. So our t obtained is negative 0.310. That falls below the mean, and we were hoping for a score well above the mean. So we are definitely going to fail to reject the null in this case, right? It seems that the manipulation of the independent variable actually had them do slightly worse. And for r squared, you just take t squared, which would come out to 0.096, divided by 4, which comes out to 0.023. Now, you can also write this as 0.02. I just wrote it as 0.023 when I was writing it. Again, t is always to 3, right? So whenever you're computing a t score, you are going to round to 3 decimal points, all right? Everything else, you have to do to a minimum of 2 decimal points, like people did on the first test. If you want to write the whole decimal point out to get the most correct answer, or if you're confused with the rounding and rather not get it wrong and write the whole thing out. That's perfectly fine. So what are we going to do here? Again, we are going to fail to reject the null hypothesis. And that is it.